Hello everyone, let's study about damped oscillation. Now there are many instances where when a body is undergoing a simple harmonic motion, in that case the amplitude will not remain constant. The amplitude will keep on decreasing. Such kind of oscillations in which the amplitude is decreasing with time is called as a damped oscillation. So for any system in the universe where there is a resistive force present, in such cases there will always be damped oscillations. A graph of displacement versus time would keep on decreasing as shown here. To understand this, if we take an example of a simple pendulum, let's take this as its mean position, and if the pendulum is pulled to some extreme end, for example it's been pulled towards here and let to oscillate, then the pendulum will go to the other extreme end. Let's call this as point B, this as point C, and this as point D. Now once we pull from point B and leave it, the pendulum would go towards the point D. But each time it is going through the atmosphere, it would experience a drag force, because of which the pendulum would still oscillate, but next time when it comes towards the point B, it will not go till point B because some energy has been lost in the process of oscillation, because of which the pendulum will go to a distance which is less than the point B. If it is somewhere here, we'll call as B1. Now this decrease in the amplitude is because of the energy being lost. The energy for a simple harmonic motion is given as half into k into a square. If energy is decreasing, if energy has been lost, then this k is a spring constant that will not change. It would imply that even a also is decreasing. Again, while going towards point D, in the process going from point B1 to point D, energy has been lost. So it will not go till point D, it will stop somewhere before point D1. So each time it oscillates, it would lose energy. And also there is energy lost at the point of, say, pivot. Even if this is ignored, still since it moves to atmosphere, it would lose energy. A graph of displacement versus time is shown here. So each time the amplitude is decreasing, each time it is decreasing. So if we connect the edges of the amplitude, this is what we get a curve like this. So such kind of oscillations are called as damped oscillations. There are many examples of damped oscillations. Practically every oscillation on the Earth's surface or anywhere on the Earth would be an example of damped oscillation. Example 1 says oscillations of simple pendulum in air. Just saw it. Example 2 is oscillations of a sonometer wire in air. Even there also, when the wire vibrates, it is vibrating through the atmosphere and it would lose energy. So even the oscillations of a sonometer wire is an example of damped oscillation. Example 3, oscillations of a mass attached to a spring and placed on a table. So when a spring is attached to a mass, and if the whole thing is placed on a table, then each time the mass moves either away from the spring or towards the spring like this, each time it oscillates or each time it moves, there is friction present between this surface and the table, because of which energy has been lost. So even this case of spring mass system is an example of damped oscillation. Other examples, the fourth one here is oscillations of a swing in air. So if we assume there is a swing, and if you pull it at this point and leave it, it's common sense that the swing may go to some point and again will not come to the same point. It's just like a simple pendulum. There is loss of energy. In fact, in case of a string, there will be a greater loss of energy because of its mass involved. So it will come till some point here and again go back to lesser amplitude and it will finally die down. Even this is example of a damped oscillation. Another example is a swinging bell. Leg to itself will eventually stop. So if you have bell also, example, think we look at a bell and then if you look at its oscillations here, if you let it oscillate, even this also would die down. So whatever is seen here is practically anything in the atmosphere would die down. These are examples of damped oscillation. That implies there is presence of a resistive force. Now damped motion is not true only for oscillations. Dampness is present everywhere. Even if a rocket has been launched through the atmosphere, it's not an oscillatory motion, just a linear motion. Even here also there will be energy lost. Let's find out what is the expression for the displacement in case of a damped oscillation. To understand this, let's recall what was the equation of a free oscillation. For example, if you take case of a spring mass system, F was minus k into x, where F was the restoring force, or in general for simple harmonic motion, F is equal to minus k into x, where k is called as force constant. And x was of the form of sine or cosine. So we can take x is equal to a into sine of omega t plus phi. We can take cos also here, it's the same meaning. This is for a free oscillation or simple harmonic motion. In case of a damped oscillation, there will be one more term because of damping. What is seen is, in most cases, the damping force is given as minus b into v, where b is a measure of dampness of the medium, which means if a medium offers higher resistance, it will have a higher value of b. For example, imagine that the spring mass system is let to oscillate in free space, and one more case, the entire system is made to oscillate inside, say for example, castor oil. It is common sense that in case of oscillation of the mass in castor oil, it will come to rest very soon. That is because of its high dampness. That high dampness is given through B. This is what is seen experimentally. If a body oscillates, if a body moves faster, it will have a greater damping force. So, to write it, the net equation, what we get here is, you would get F is equal to minus kx into minus bv. Remember, this is the net force on the object. Both the restoring force and damping force are both negative force only, so it is a minus sign here. If you rearrange it, then what you get from here would be like this. That is, we got F is equal to minus kx minus bv, but F itself was equal to m into a. Since we assume it is a one-dimensional motion, we can write a as a is equal to d square x by dt square. So this would give us m into d square x by dt square is equal to minus kx minus bv. We'll bring the terms this side. Then what we get from here would be d square x by dt square plus b by m into v plus k by m into x is equal to 0. So m is being brought down and then the two terms are brought this side. This is what we get. To rewrite this, you can say d square x by dt square plus, there's a constant here, it's called as 2c into dx by dt plus omega naught square into x is equal to 0, where b by m is called as 2c, one more constant because both b and m are constant for given motion, and omega naught square is equal to k by m, which is called as free oscillation frequency, angular frequency. The solution of this is not required for this level because this is a second order differential equations. There are many ways to solve this expression. The proof of this is not required for this course. So what we'll do is we'll directly take a solution for this and we'll try to verify by putting that in this expression. To solve it, the solution to this is of the form as given here. It's of the form x is equal to, it is a into e power minus bt by 2m cos of omega prime t plus phi. This is called as omega prime or omega dash. This is what is a displacement equation. When you solve it, if you want, you can go and verify this. We can put the values of x in the expression as given here. We call it as expression 1. If we put it back here, then we should get 0 on the right hand side. That is what is the expression in this case. Now that omega prime, what we saw, it is equal to k by m minus b square by 4m square. As I told you earlier, this has not been proved here. Just learn as a fact. The proof is not required. Just to recall it, x is equal to a into e power minus dt by 2m cos of omega prime t plus phi, where omega prime itself is of this form. Now recall what was x for a free oscillation. So x of t was equal to a into cos omega t plus phi. Whether it's cos or sine, the form is same only. Don't get confused because sometimes I would write sine, sometimes cos. The idea is the same form. It depends on the factor phi here. This phi will take care of it. Now compare this and this. Suppose if we take a case where b is equal to 0. Now b is 0 would mean that it is a damped free medium, which is same as free oscillation. When you put b is 0, then this term goes to 0. And also here, this term would go to 0. In that case, omega prime becomes same as omega naught only, which means this expression of x for damped oscillation will give us the same value of x for a free oscillation when you put b is equal to 0. So you can think that the free oscillation is a subcase of a damped oscillation. You can think that way also. This is what we get in case of a damped oscillation. If we draw a graph of displacement versus time, as seen earlier, we'd find a case where the amplitude keeps on decreasing with time. After some time, it will decrease, at some point it will die out. But then that is a long time die out because of the form that x of t is a into e power minus bt by 2m cos of omega prime t plus phi. This exponential function, this function would become 0 only when t becomes infinite. So even though it's a very long time, it will have very, very small amplitude you can't recognize. For example, think of a spring mass system or a swing. Think of a swing. If you leave it, we would assume that the swing comes to rest. But actually what happens is the amplitude will be so small that you can't recognize it. But theoretically, this xt becomes 0 only when t tends to infinity. It will have very, very, very small amplitude which you can't observe. The behavior that this amplitude keeps on decreasing, this behavior is a exponentially decreasing function. You might have learned in first chapter that this function, the curve of this form, this means it is an exponentially decreasing function. If we plot a graph of x versus e power x, this is what we get. It will keep decreasing exponentially. That's the reason we get a graph like this. In terms of energy, we saw that in case of a undamped oscillator, the energy was given as half Ka square, which is always a constant. For a damped oscillator, we're not proving it. In this case, energy is a function of time, and that is given as half Ka square, this factor as it is, into a factor which would decrease energy exponentially, because each time a body of example, say like a spring mass system, each time it oscillates, the mass moves to atmosphere, because of which it will lose energy. So energy keeps on decreasing. That is shown by a factor of E, which is decreasing exponentially. That will be minus Bt by M. So the energy also would decrease exponentially. If you plot a graph of energy versus time, even there we get a graph like this, which will keep on decreasing exponentially. So the total energy would decrease exponentially with time. As seen earlier, if we take B to be 0, which means it's an undamped case, then this term tends to 0, and what we get would be this only, which means an undamped case is a special case of a damped oscillator. Even though we take it for a spring mass system or a simple pendulum, the basic idea, this idea remains same in every kind of a simple harmonic motion.